Hello, and welcome to the OpelX podcast, bringing you candid and open discussions about all things in the power electronics world.
This show is a part of the Open Power Electronics Network. Visit us online at opelex.net. That's opelex.net for show notes, articles, tutorials, and a whole lot more.
My name is Abhijit Kshirsagar. Currently, I am a professor at the Indian Institute of Technology, Dharwad, where I teach and conduct research in the Electrical Engineering Department.
And I am Lalit Patnaik. Currently, I am a fellow at CERN, Geneva, where I work in the Beams department designing power supplies.
Lalit and I were colleagues at the Indian Institute of Science, Bangalore, where we both completed our MTech and PhD degrees in the Power Electronics Group at the Department of Electronic Systems Engineering, DESE.
Over the coming weeks, we will be talking to leading academics, industry professionals, entrepreneurs, and other leaders in power electronics and allied fields. We hope you will find this useful and entertaining. So sit back and enjoy.
Hello and welcome to another episode of the OpelX podcast. Today we have a very special guest with us, Professor Ashwin Khambadkone from the National University of Singapore, who's currently in India. Professor is at NUS Singapore, where he teaches electrical engineering, power electronics and related subjects. But over the last few months, he's also been teaching as a visiting professor at the Indian Institute of Technology, Bombay. That's IIT Bombay. Welcome, Professor Khambadkone.
Thank you.
So just to elaborate on that brief introduction, could you tell us a little bit about your role at Singapore and what you're doing at IIT Bombay?
In Singapore, I started out at National University of Singapore as an academic. In 2010, I took over the role of program director of an experimental power grid center, which was a national research institute or a national research center, where I was leading a team of researchers, and the objective was to interact and support the local industry working in renewable energy area. Since this was a joint appointment and a fixed time appointment, I was required to return back to National University of Singapore. And so 2016, I returned back, where I was heading a research project on solar irradiation prediction. Again, problem of solar PV integration, how it impacts the grid. And then by 2019, beginning of 2019, I came over to IIT Bombay for the visiting position. At IIT Bombay, I gave a series of lectures on electric vehicles and their integration into the grid, because I felt that that problem would be soon appearing on the Indian scenario. And so we looked at the general part of electric vehicles and then how they impact the grid. And that has also been the area of my research for this period when I was in India. Roles pretty much like an academic in anywhere else, but the difference is that all throughout my career, I have always interacted very actively with industry. Even during my PhD days, I worked very closely with industry. So it has helped me develop a different perspective than a pure academic.
And your PhD was at Wuppertal University, right?
Yeah, I did my PhD in University of Wuppertal with Professor Holtz, one of the leading labs in power electronics and drives in the 90s and very until recently also. The German system of PhD is very different from what many people know in the Indian or the Anglo-Saxon universities. So there we work on research problems. We also work very closely with the industry.
That's great. Can you just elaborate a little bit about your research vision? You mentioned PV integration in grid. You mentioned electric vehicles and their impact on the grid. I think you have a very holistic view of big picture problems that our grid and our power system is going to face in the near future. So can you just comment on what you think the big picture problems are and how power electronics and energy systems sort of fit into that big vision?
Yeah, I mean, this COVID-19 situation has already given us an indication of how quickly the environment can heal itself. I mean, if you see some of the pollution data over some of these regions, the exhaust gases gone out, you can really see the drop and clarity of the quality of the air has improved. So it already gives us an indication that going for cleaner technologies, both in transportation as well as in electrical energy generation, is something which we should aspire very strongly. And I think that this will happen very soon. So where is the problem? Problem essentially is that these are what are called as non-dispatchable generation when we talk about renewable energy. And the electric vehicle on the other side is a load which is whose behavior is not yet very clear. See what happens in a power system, the basic challenge is that you have the load which has to be predicted. The load is supposed to be the uncertain part of the system. And as the load changes, your generation has to follow the demand. So that's basically the principle of keeping the power balance in place. And that gives stability to the system. This is one form of stability. Generally, basically, you have to always balance the generation and the demand. Now, in case of renewable energy, there are some cyclic patterns, but within that, there is a lot of variation. So typically, a renewable energy source is both variable and uncertain. So variable means it is not within your control and keeps on varying. And uncertain because you cannot really predict a particular value on a particular time during a particular day. So in terms of the whole operation of power system, this becomes a challenge. Now, you may think that, power electronics, we generally think that it's only the power electronics which comes in terms of converters, which is going to help the renewable energy. But integrating renewable energy into the grid is a very, very important system issue, which has got multiple factors. The obvious answer is that if we can predict this uncertainty in some form, then we would be able to control the system better. So you can start seeing already the importance of data, big data analytics, predictions, machine learning, and all that coming in here. Now, one way of correcting this uncertainty in generation is by using energy storage, which is sort of dispatchable and gives you some level of flexibility in the system. But controlling that, again, energy storage is typical energy storage, which is now used, is the batteries are coming in. Lithium-ion batteries, you must have seen Tesla putting large battery banks in Australia to control. Now imagine you have a variable demand, variable generation, and your control which will come, the flexibility will also be variable. So if you're linking the battery to the power system, which will happen through a power electronic device, it will need a control which is again able to predict, understand, behave, and so on. So there are multiple issues now in different time scales. So there is a short-term issue. You have to supply so much amount of power in a certain time duration. That is a control issue, real time. Most power electronics engineers are well aware of this. But then how do you generate the reference for it? Then comes the longer period of prediction. Then there is a whole system issue, whether you're doing it efficiently, cost effectively. There is a much wider time scale. So you can see the time scale goes from milliseconds to months and years.
Right.
So it makes this problem quite interesting. The same thing will happen for electric vehicles, but on the load side.
So, Professor, the question that I wanted to sort of pose to you is, you've sort of addressed storage as a solution for addressing the unpredictability and variability of renewables. Do you think that there are non-engineering solutions to address the demand side? Looking at data, trying to change behavior, demand, because electric vehicles, it's always a choice whether you drive or not, whether you go now or you go later, right?
Well, I wouldn't call it non-engineering solution because when we solve a problem and come up with a solution, that is an engineering solution.
Yeah, that's a good point.
It may not be a technology-based solution. Technology means completely like a hardware-oriented solution.
I see.
And I'm not saying that battery is the only solution. So one can do many things in terms of demand response, time of charging, time of use, and so on. So the whole thing becomes a highly integrated, system where you need data, you need prediction, you need social behavior comes into pattern. Because like you said that you can drive, you have a choice of driving. Sometimes you may not have a choice of it's a personal preference.
Right.
That's a social behavior which comes into picture. And then most of the electricity currently is market driven, market based. You will practically have a choice. If you want to buy and charge it very fast at this time, it may cost you a different rate. Or if you are ready to take care of what is called as an inconvenience factor. So you say, no, I don't want to, I have parked, but I can drive after an hour. That choice is available to you. So it's sort of part of that larger concept of smart grids. Again, we have to approach this problem not purely from engineering or technology based, because one could always come up with saying, I'll give you a choice, I'll give you an app, you'll get on an app, you will get this choice and so on. But imagine if you are sitting there doing some important work, every now and then you get this messages which says, do you want to charge? Do you want not to charge? And so on. That is also not, so one has to keep in mind the behavioral aspects because humans are interacting with the system. So I have seen many solutions in smart systems where they always say, okay, you have a choice, you can choose when to buy and so on. You don't need that. When humans interact with commodity, we have been doing that, and we are not always. If you have been investing in the equity or shares or in the whole stock market, you don't sit every day and keep on watching what's happening to Sensex, right? There are different plans and so on. So you can see how there is a solution even at a management level, aggregation level. Systems get aggregated. Then you have to find the best case choice and so on. So this makes it much more than just a couple of switches and PWM and control and that sort of thing. So it's not just an electronic solution, it is a system solution. And that's what is happening to most of the technologies. There is a heuristic of how systems develop, technology systems develop. So initially, if you look at the early part of technology, where take it a bullock cart or a horse carriage or something, a lot of use of human or animal power and less of intelligence. Means every time the user has to interact and make choices. As systems evolved, you will see they carry their own energy source and they have much more stored energy. In fact, automotive, basically the word tells you that it is on its own. It's carrying its own power supply or power. The choice was that you were making the choices, whether it was steering. And then if you see how the cars evolved, lot of systems, you didn't have to think. They happened in the background, they were automated. And then we are talking about self-driving car which is driving on its own. Be it a communication system, be it a production system or any system, if you see, systems become power independent, they become more complex, they can take their own decisions, but they interact and serve a purpose. So that's what is happening to most of the systems. And that means that the old way of doing engineering has to change. The old way of doing engineering was looking into very specifics and saying, okay, I need to be expert in this area and I don't care what happens in the other area and so on. But here, because we are talking about a whole system, we need to understand lot of other things which are happening around. So like in smart grids or electric vehicles, you have to talk about behavior, you have to talk about environment, you have to talk about reliability, you have to talk about recycling processes, costs, economics, all these things. So that's making the system more interesting, and it's making engineering more interesting.
Professor, you very nicely talked about the complex systems thinking aspect of it, as a power electronics engineer, it's so easy to just get stuck up in circuits, but basically we are talking of a very complex system. So when we think of such a scenario where it's not just circuits and we have to look at the economic side, the human behavior side, software or data analytics side, and so many things, how should the students of today prepare themselves for these kinds of future careers? What skills and what subjects do they need to master?
We have been looking at education aspect also, and we are realizing how our old curriculum style does not really help. The old curriculum style sort of assumes that, okay, I will give you the building blocks now, and then after 4 years you can put it all together, and you will get an idea later on. And then once you go into the company, they will tell you, or once you go to work, you will understand it better. Modern workplace is not going to be like this. As soon as you join a workplace, you will have to work on complex systems. That means you will have to know what other parts of the systems are doing. In fact, one of my tasks when I returned back to NUS was setting up the first year curriculum which addresses this issue. And so what we did there were, we introduced, right, for the first year students, we introduced engineering systems right in the beginning. Mm-hmm. So it was not about, you learn differential equations first, learn Kirchhoff laws and Laplace transforms first, and then you will understand what's happening. We start top-down approach. So if you say, okay, electric car, right? Purely from functional aspect, you can start thinking about that system. You may not know the technologies, but you know the functions, right? Or a mobile phone. You know that it has to do the following functions, provide voice communication, data communication, video communication, and so on. So you start putting all these things into boxes, let's say a block diagram approach. You break down the system. So you can start understanding the system based on its functionalities. And then you can keep on questioning. Okay, when I get let's say it has to do some audio signaling, but finally this information has to be transmitted somewhere. So it has to finally go into electromagnetic waves, right? So what is the process of converting that sound wave into electromagnetic wave, or a picture, how the picture has to be interpreted? So we start thinking in a systems point of view. And what I have found by my own experience when we ran this first year module is that the students are capable. It's not like you have to know Laplace transform. In fact, the problem is they keep on asking, why should I learn Fourier transform? Why should I learn Laplace transform? Mm-hmm. But once you introduce them this concept, right, we started discussing this. I'll just give you an anecdote. This group of students was talking to me and they actually raised this. I mean, we are learning Fourier transform in maths and we really don't understand why we need it, right? So I asked them, let's say mobile phone or some Alexa or this type of thing. So a person is talking to the phone and the machine now has to understand whether it's a male voice or a female voice. So I asked them, how do you differentiate between male voice and female voice? What is their own experience? Intuitively, what they will. Mm-hmm. And so they said the frequencies are different.
Yeah.
Male voice is a lower frequency components will be higher. Female voices would be more higher frequency. So then I asked them, how do you differentiate these frequencies? Mm-hmm. Let's say you got some sound signal. So we actually started having this discussion. Okay, sound signal, what would be the signal? What it's a time-based signal you get, and then from there you have to get frequency. So they say, now I understand why Fourier series or Fourier transform has to be used, because now it will tell me how to separate the frequencies, and depending upon what frequencies are available, I can make a decision. Now the decision-making part is where machine learning would come in and so on, right? So in this discussion, they started seeing the whole meaning of where these subjects fit in. And so when they go back, they go with a different view. And this will be a challenge for the lecturers now. They can't push some favorite equation of theirs down the throat of the student. The student will ask that, no, you tell me how to identify the frequencies in the, these frequencies in the voice. So it will be more application oriented. Mm-hmm. Well, the purist would say, then what would happen to the thinking and, higher skills and so my point is that if you just keep on pushing theory down their throat, we know that they are not thinking, they are just going through the motions, right? So now when you approach from the system and ask them what is needed, they at least started thinking. I'll give you a second anecdote to illustrate that how even at that point, they can on their own come up with higher level thinking. So this is an example anecdote what happened in our first year module. We have actually combined electrical and mechanical students. So the concept is systems is multidisciplinary. So why should the students, the electrical and mechanical or other areas should not combine? So they were combined. So these are a bunch of electrical and mechanical students, and we were looking at complex phasors, which is used in AC circuit analysis, right? And it's for most of the students, this is a bit of a difficult concept, the complex algebra and so on. So we did this example, and then we basically said that these are 50 hertz phasors which are rotating. That comes from the way the motor runs and so on. So that was told to them. And then these phasors become stationary if you start moving with them at the same frequency. So at 50 hertz, you move with the same 50 hertz, then you will have this phasors as stationary. And now what happens is the different phasors, the relative angular displacement tells you the relationship. So that's how you get the whole complex phasors analysis, right? So they understood this. This was not told to them very mathematically, but we combined the physical picture of this, analogy of this with this. Now this mechanical engineering students asked me this question. So it would mean that the harmonics cannot be shown on this. See, this is a concept which even power electronics students in their, when they come later to do their PhD will find it appearing first time in their operation, because our classical textbooks only teach 50 hertz, right? But we were already doing this system based, so they were already measuring things which had harmonics. So they asked, what is this? This is harmonics. And what is harmonics? Then they know from there's a multiple of base frequency and so on. So once you know that it is rotating at 50 hertz, the harmonics appear at different frequencies. They are not stationary. They are rotating. And so I was, for a moment, taken aback. I said, what a fourth year student or a graduate student learns in a classical curriculum. This is a first year mechanical engineering student asked me this question. So what I'm saying is that such approach does not stop you from thinking. We are all thinking people. If we have enough curiosity and basic thinking intelligence is there, otherwise you would not have come to engineering, right? So with that basic IQ and this curiosity, people do apply and think at higher level. So it allows you to. So I would say that ask questions. So what should students do? Then you just don't study for exams only, or just look at your own circuit, but then ask, okay, why, where is it being used? How is it linked? What will I do? And try to relate it to your experience. You are using a mobile, all around you there is power electronics. There is power electronics in mobile phone. There is power electronics in your battery charger for your computer and so on. Start asking questions. Why does this get hot? What would happen? Can I operate it at other voltages? You take a battery charger and for your laptop, does it only work? Can I use a battery charger which I bought in the USA in India? What should I look for? And so then the power electronic design tells you that it is not just designed for 110 volts or 120 volts, like the old transformer, which was in the pre-power electronics era. You designed a transformer for a certain voltage to step up or step down. But power electronics change the frequency, so it does not matter, right? And stepping up, stepping down is done by the converters. So then you would ask, what would be the design range for this? And then there is a requirement. There is a universal voltage range for a power supply design, which goes from 265 or 285 lower, close to 100, less than 100, right? So wider the range. So then the question is, if my power fluctuates, is my device going to have problems? Voltage sag problem, will it be there? So once you start connecting the dots, your general awareness of the system increases. But if you just look at, okay, I just need a rectifier in the beginning and the formula for rectifier is just this and this, and then convert to this voltage, then you are not really thinking at that higher level.
Right.
So I would say that whether it's power electronics, whether it's some other thing, you always start thinking, connecting with the rest of the system, your own use, and start thinking at a higher level by asking questions. Why is this needed? What is the range, and so on.
So students who are either at NUS or IIT Bombay, of course, have a very great place to ask these questions, and they benefit from your experience and all these sort of new design of curriculum that you have been espousing. What about students who are not at these institutes or elsewhere? What are some good resources for them to, of course, they can ask questions, and what are good places for them to find answers? What are some good resources that you would recommend to other students?
First is, let's talk about an entry-level student. So in an entry-level student, one has to ask this question, why am I here? If I've come to do engineering, I would have certain goals, right? Mm-hmm. Based on that, there's so much of information which is available. Today, we are in an information-rich world. Mm-hmm. Look at IEEE Spectrum or some of these, if you are interested in a particular area, there are technical magazines or don't try journal in the beginning, because that will just make things very complicated. But there are electronic magazines which are there, whether it's power electronics, whether it's any area you pick up. There is not a trade magazine, but technology magazine. You can start there. Then okay, this is my area of interest, and these are the technologies, how the technologies interact with different things and so on. Because we are living in an information-rich world, our attitude should be, first, I have to learn to ask questions. Second is, I have to learn how to prioritize the questions. Because we are so information-rich, you just keep on trying to search answers for all your questions, you will be lost. And you will waste a lot of time. So prioritize it. What is important for me now, right? Someone might feel that exam is important. I'm not saying exam is not important, but then if I am to understand a particular subject, I want a certain level of mastery in that subject. I should focus on understanding the core of that subject and core meaning of the subject. One of the things which, the way I approached my own way of acquiring knowledge in the days prior to Google and others, was first try to get a layman's view of the system. Can I explain this working of an induction machine to a non-engineer? And this is not me, but a lot of people have, I think Lord Kelvin or someone has said that if you can explain it to your grandmother, then you have understood what is happening. So try to understand any system or a subject in a way where you can explain it to someone who doesn't know engineering. Then okay, I know what is happening here. Then the rest is all making the picture finer and, adding bells and whistles and so on. Right?
So I think those are some very good inputs. We are going to have a show notes section as well. And some of these links and, these resources that we are mentioning, we'll put links to those in the show notes.
See, I'll give you an actual example which I use.
Okay.
When I teach power electronics at undergraduate level, in Singapore, not many people know what an inverter is.
Yeah.
In India, I expect a lot of people to know at least the name inverters. I even joke that in my class, saying that in India, even a grandmother knows what an inverter is, because UPSs are quite ubiquitous in most of Indian cities also. So we start there, what is inverter? We have a discussion. And during that time, inverter-based air conditioners were a big thing. Had a lot of advertisements, commercials from various manufacturers. So we started questioning, what is this inverter? What is it doing in the aircon? So we went to how stuff works and then found out how basically this aircon works. And then we realized, the aircon needs this compressor to be driven, and then there is a fan unit and so on. And then we kept on going. Once we realized that we had to do speed control of the motor, then we kept on going that way. And eventually, after the principle and all was taught, we actually went to the websites of many of the power electronics component manufacturers and then looked at their offerings in terms of IPMs, intelligent power modules and chipsets, which are specifically meant for air conditioners. Then we found out refrigerators and so on. So many a times, electrical engineer may not think about how the refrigerator works and what it entails, right? Why this was very interesting for us is because when we came to smart grids, this knowledge was very important, because we knew that the refrigerator and the aircon could work on both AC and DC. That's how is an example of how one can go about finding out how things work and how to connect.
So I think we can have a long discussion about your innovations and views on education and reforming curriculum. But in the interest of time, we are already running a little bit behind. Can we just talk very briefly about some of your industrial experiences? Can you tell us a little bit about one interesting experience or a learning opportunity that you had as a result of an industrial project or an industry interaction, just very briefly?
Well, when you work in Germany, you're an assistant to the professor. You are not just doing your PhD, you're doing so many things, helping in the lab and so on. So we were doing industrial projects, and I was doing vector control of induction motors. By that time, the patent had lapsed from field-oriented vector control, and many small-scale and medium-scale industries were wanting to get into the technology. The way one has to approach the industrial project is the actual control is only a small part of the whole system. Lot of effort and lot of what really takes time developing is the periphery, the protection systems, the user interfaces, and so on. Of course, we didn't have to focus on that, but we had to look at the parts which took the space and time on our processor. Another part was that you can't just pick up a micro P in the market or a DSP in the market and just say, oh, I don't care. The DSpace type of approach, I really don't care how the system, how fast my system is. Because in the practical system, those days at least, the computing power was not that great. So you had to get down to really assembly level and then program it. There are other practical difficulties. In a lab type of situation, your focus is somehow get the work done, try the best control algorithm with complicated, but there, you would have restrictions. So most important part is sitting and understanding what the customer needs. So this was done by the company, but when they do it, they actually take the customer requirements and break it down to the technological requirement. Let's say the customer said, I need speed accuracy of so much percentage. Then you have to get down to a level where you say, how many bits should my A to D have, or speed sensor should have, and so on. It's not just getting the best algorithm or taking MATLAB or some ready-made thing and then doing it. Those days there was no such thing available. So it taught me actually to go through the whole process systematically and understand its implication. There are thermal issues. There are things which you have to put in there, which you never learn in a textbook, or no research paper talks about it. It's the thermal aspect of your control, because your drive operates at different regimes. And at different regimes, based on the thermal loading of the devices, you may or you may not be able to operate at full current capacity. These are not standard algorithms. So, it is not like you pick up a book on vector control and you learn. We also did self-commissioning. There were quite a number of papers on self-commissioning, which took an approach of finding the best algorithm to find the best parameter and so on. But in practice, what happens is many of these companies are not investing heavily in the processing speed. I mean, those days, now the processing speed has increased. So within those constraints and the actual application, what you realize is you need a system which even a technician can operate. You should not design a system where you require a PhD to commission it. That's too costly for a process. So this is one thing one has to understand when you look at actual engineering system. You can get the best algorithm, complicated algorithms, and so on. But if you need a very advanced level person to commission it, it costs. So there are multiple things how we have to go through a process and so on, because a lot of the problems which happen. I'll just relate to you one thing which I used to do. So in Germany, when we were doing this, we also used to guide undergraduate students and master's project students. So many of the students used to work with me. So I used to have this process where at the end of the project, when they feel that they have done all the software, all the results are there, we would have a long duration run. So we would come in the morning. I would ask them to turn on their drive, and we would have a signal generator which runs the drive through different regime, and it has to run for the whole day without stopping. Now, initially they are scared because, while testing and doing their work, they run for a short time, they got the result and just happy about it. When we force this, two things happen. The bugs come out And if there are no bugs and it runs, it gives them so much confidence. Many of them actually when they went for the job interviews, they were so proud of what they did and they were so confident that they were able to develop a system which does not break within 5 hours or 6 hours. They would then proudly come the second day and run it. Later part of my career, when I was heading the Experimental Power Grid Center, working with the industry, one realizes that listening to the customer, listening to the problem definition is a key part. You are not trying to sell your solution. You first understand the problem first, and then you come up with an appropriate solution. You should not try to peddle your solution just because you have developed something. It may not be best solution for the customer. The third part is the multidisciplinary approach, because especially in energy, there's so many other things which go in. You need to have a good understanding of what thermal behavior, you need to have a good understanding of economics, you need to have a good understanding of other communication, signals. Many of these systems are all automated, so you need to have a good understanding of the information layer. I think the approach for me for learning is there's so much one can learn by just keeping an open mind, asking questions, and not trying to push your agenda. Many a times I have this scheme, I want to push this, but listen to the people and then learn and then adapt. And sometimes together you can come up with new solutions. But the key aspect is that my approach to research has changed. So my approach is not about I have to publish a paper, or this whole chase of running after a novel idea. Okay, many a times we get into this trap. You have to first start with a problem. You have to understand the problem. What you want, a desired outcome, is not possible given the actual constraints. Now you have to work in that space, then find a solution within that space. You can't just go and say, oh, here I have got an innovative idea, you can use it. It may not work at all, you see, or it may be too costly. I look at research problems rather than research techniques or research methods or fads or whatever you can call it, right? I try to ask this question, what is the key problem here? And then go about solving.
We have had such a wide-ranging conversation covering the education, the research, the products, and let's say industry side of all these power electronics projects. Just to close the whole conversation, would you like to mention some of the places online or where people can find your work?
Many of my publications are available most of them are published in IEEE or other journals, and they are accessible externally. If you Google for my name or go to IEEE, the papers are available. But the papers only tell you a small aspect of it. The rest of it, what I've discussed, cannot be captured in the paper. Right? But if you look at many of my papers, there is a pattern. What I've just mentioned comes out in that fashion. So some of the work which we have done in overmodulation, this area was very new, and the problem has been identified and then a solution has been proposed. That was energy storage, composite energy storage concept. So that's another area. Recently, there are some papers on electric vehicle, smart car park. And one of my PhDs who has just completed, he has worked on integrating PV and the problem with managing the set points of the tappings of the transformer. So these are all published material, so it will be available.
Thank you, Professor. It's been a really great conversation. Of course, students can find you through your academic profile on the NUS website, and I'm sure you're listed on IIT Bombay website as well. Is there any other comment or final advice you'd like to give to all the prospective students and young engineers who are listening in to this podcast right now?
I think the advice is not very different from what is generally given. It is to basically get one's priorities right. Once you set your priorities right, then automatically you would know what are the things you have to focus on, and then slowly go about doing it. Once you know this is my priority, then dedicate full effort towards that priority. Don't overdo things. That's the reason why you prioritize. There's 3 most important things, and then you go about doing it.
Okay. So once again, thank you very much, Professor Khambadkone. We look forward to speaking to you again. Have a great day.
Thank you for taking time to manage all these things. You're doing a great service to the student community and the future power electronics and power engineers. I am glad to see such an initiative being taken. I think it is important. There's a lot of information available out there, but it is important to curate that information and present it in a way which is advantageous to this student community. Keep up the good work, and I'll be glad to share and cooperate with any of your ideas in future also.
Thank you.
Okay, keep safe.
Thank you so much.